Welcome everyone. For today's prep, we're going to see some examples for how to graphically find where our function is concave up and concave down. So we've looked at the definition, we've looked at some examples. Let's just read through one more definition here, and that is for what we call an inflection point. So an inflection point, well, it's a point on the graph where our function is continuous, but more importantly, it's where it changes concavity. So we go from either concave up to concave down. All right, so how are we going to find these? If we're given the graph of a function, how are we going to find the intervals of concavity? Well, our strategy is to look for kind of the places where our function has a kind of a big bend. So for concave up, what's the kind of the classic example of a concave up curve? Well, it's a parabola that opens upward like this. So this is concave up. So we see a kind of a big bend in the graph here. And you can test it, pick any point on this curve and draw the tangent line. And what you see is that the curve itself is going to bend above the tangent line. So it's concave up. And a way to remember this, it's concave up like a cup. So you could imagine filling this up with some water and it would hold the water. It doesn't have to be the entire shape like this. It can be just part of it. So it could be maybe just like the left side of the shape, or it could be just the right side. So something like that. So those are all examples of sections of a curve that are concave up. Now concave down, again, we're kind of thinking, what is the classic bend shape going on with a concave down curve? Well, the way you can remember it is concave down like a frown. So a little rhyme there. And it's the upside down shape. And it doesn't necessarily have to be the entire thing like that. It could just be the left side or just the right side. Okay. So the idea is when we're given the graph of a function, we want to look for these types of bends in our graph. So let's try an example. Let's look at example 2. So for this example, we're given the graph of some function y equals f of x, and we want to find the intervals of concavity, and we also want to find all of the inflection points. So the way we're going to do this is we're going to start by looking for those kind of sections of the curve where there's a lot of bend, where there's a lot of curve. And when we look at this, kind of see two sections. So I see the section right here where there's kind of a lot of curve. And then also see the section right here where there's, again, kind of a lot of curve going on, a lot of bend to our graph. So then you want to think, well, what shape do each of these represent? So if we kind of go back up, we look for think about the one, and, well, this one matches up with this section right here. So this curve, this section has that kind of classic concave down bend. You can also test it by picking a point, drawing the tangent line, and what you see is that the curve itself bends below the tangent line. So this section here, we would say, is concave down. Has that concave down look. Well, what about the other section? So this is our kind of our shape here. So if we kind of go back up to the options, look for the corresponding option or the matching option, and we see it right here. This is the one that most resembles our shape, and that's concave up. Another way to think is if we're back at that point or back at that section, pick a point somewhere in that section, draw the tangent line, and in this case we see that the curve itself bends above the tangent line, so it's concave up. So this section is concave up. Now what happens is we have one section of our curve here that's concave down, another section of our curve that's concave up, and we have this kind of this place in the middle where it's kind of hard to tell what the shape, how the graph is bending. So not to say that it doesn't have any bend to it, it's just kind of hard to tell because we're looking at a graph. The changes are kind of small there. But what happens is in between these two sections, where one section we're concave down, the other section we're concave up, there's one specific point in the middle there where we actually change concavity. And if we had to kind of estimate that, I'd probably put it right around there. And we give such a point a special name. We call that's our inflection point. So it's the one specific point on our graph. Well, it might have more than one inflection point, but it's the one specific point in between these two sections where we change, in this case, from concave down to concave up. All right, so what does this inflection point do? Well, it splits up our x-axis. So it looks like this point is happening at 2, maybe 1.5 if we had to estimate. So let's record that. I think we wanted to find our inflection points. So there's only one of them in this case. And when it asks for points, it wants the x-coordinate and the y-coordinate, so 2, 1.5. And what this inflection point does is it splits up our x-axis. So we're splitting it up at x equals 2, and we have this section of the x-axis before x equals 2, and we have this interval of the x-axis after x equals 2. And what we found is that for this interval, that's where our graph had the concave down bend. And for this interval, after x equals 2, that's where our graph had the concave up bend. So what we found is that f, so for our intervals of concavity, we found that f is concave up on the interval, 2 to infinity, and f is concave down on the interval minus infinity to 2. So the inflection point there is kind of where we're splitting these intervals up. All right, so let's try another example. Same setup here. We're given the graph of a function y equals f of x, and we want to find, again, the intervals of concavity and then any inflection points. So, again, let's kind of focus in on the graph here. And when we do this, we want to look for the sections of the graph where there's kind of a big bend, big curve to it. And when we look at this, I kind of see, for this graph, I see kind of 3 sections. We've got this section of the graph where there's a lot of bend going on. We've got this section of the graph where there's, again, kind of a big curve to it. And then we've also got this section of the graph. So we've got these 3 separate sections here. And we want to identify, well, what shape do those have? So let's start with the first one here. Pick a point, draw a tangent line, and we see that our curve bends below the tangent line. So this section here, we would say, is concave down. Go to the next section where there's a lot of curve, a lot of bend. Pick a point, draw a tangent line, and we see that our curve bends below the tangent line. So it's also concave down here. And then if we go to our last section, this has that kind of classic concave up shape. Looks like you could fill it up with some water there. So over here, our graph is concave up. All right, so we have this one section where we're concave down. We have this other section where we're concave up. And it's kind of hard to tell exactly where it happens, but there's one specific point in the middle where that concavity actually changes. Again, that's going to be our inflection point. So, when it starts to look like a line, it's kind of hard to tell where it happens. So try your best to estimate. So if I were going to estimate here, I might say, maybe that point. Seems reasonable. You might say something like here, maybe over here. Try your best to estimate. So it's kind of hard to tell. We're just reading graphs. What we're going to see, though, is there's ways to figure out where that inflection point happens exactly. All right, so let's say that seems reasonable. So that's going to be our inflection point. And that's the only place where we could have an inflection point, because here we're concave down, here we're concave down, and the only place where we can actually change concavity is going from this section to this section. So what is our inflection point? Let's actually estimate the coordinates here. And again, it's asking for the inflection point, so we want the x coordinate and the y coordinate. So the x coordinate here looks maybe like 1.5, maybe 1.6. We'll say 1.6. And then the y coordinate looks to be, it's a little bit less than -1 there, so we'll say -1.25. So that's our inflection point. All right. So now what are the intervals of concavity? Well, we want to think about these inflection points, and what they do is they split up the x-axis for us. So we have our x-axis here going from -infinity to +infinity, and the inflection point is splitting up the x-axis for us in terms of concavity. So we know we have this section over here where it's concave up, and then we had this section over here where it was concave down. But there's one other point that we have to consider in terms of splitting up the x-axis, and that's this non-differentiable point. So what happens here is this is a point on the graph. We have a cusp. It's non-differentiable. So when we have a non-differentiable point, the concavity is undefined at that point. And the reason why it's undefined is because the way we define concavity, we're defining it relative to a tangent line. So whenever we're trying to decide on the shape, we pick a point, we draw the tangent line, and what has to happen is the curve has to either bend above or below the tangent line. But the main thing there is that we have to be able to draw a tangent line. And drawing a tangent line means the function is differentiable. So at this point, it's non-differentiable, so we can't actually draw the tangent line, so concavity is undefined. There's kind of... The tangent line kind of wants to do two things here. It wants to follow the right side of the curve. So if we kind of drew the tangent line relative to the right side of the curve, our tangent line would want to look like that. But if we drew it to the left side of the curve, it would want to look something like that. So there's no clear option for what the tangent line at this point is. So it's non-differentiable there. So that means the concavity is undefined. So if we think of our x-axis, let's draw the x-axis down below. So we're going from -infinity to +infinity. And what we found is that there was two places where we had to split it up. We had to split it at, where we found the inflection point, but then also at -1. So -1 was the non-differentiable point, and then 1.6 was our inflection point. So what we have here is 3 intervals. And if we look at our graph, on this section of the graph, that's where we said it had a concave down bend. So what we found is that f is concave down on that first interval. Then on the next section, we also said it had a concave down bend to it, so concave down. And then finally on that last section, on that last interval, our graph had the concave up look. So we can write down our intervals of concavity now. So f is concave up, and we found it concave up on one interval, 1.6 comma infinity. And then we found that it was concave down on 2 intervals. And we got to split these up. So we have to go from minus infinity to minus 1, and from minus 1 to 1.6. So we have to split them up at -1, because at -1, this graph does not really have any concavity. It's undefined. All right, so we're going to see in class how to do this type of analysis, but using derivatives. So rather than, trying to estimate where these inflection points happen, we'll be able to see how we can kind of calculate these precisely. So we'll see you then. Bye-bye.